Okay, so now we're going to talk about a certain type of mechanical wave, the transverse wave. A transverse wave is a wave in which the particle motion is perpendicular to the energy motion. So I've kind of already talked about it a little bit, but I'm going to talk about it some more. This is a periodic transverse wave. Let's just do a regular transverse. This is a transverse wave pulse. Why is it a transverse wave pulse? Well, if you look at this particle here, it's going to move vertically, up and down. But the energy, the disturbance in the string, moves to the right. So the direction that the energy moves is to the right, the direction that the particle moves is up and down. So this is a transverse wave. The particle motion is perpendicular to the wave motion. Okay, that's what makes it a transverse wave. Now, the wave displacement and particle displacement are important to understand and remember for a transverse wave. The wave moves to the right or left, while the particle would move up or down, if we think about the example I just showed. Now, particle displacement is related to amplitude. Okay, particle displacement, and I'm going to use this diagram here to talk about particle displacement and amplitude. So that's what I'm talking about. I'm going to jump to here for a second. So what these are, all these particles right now are in their equilibrium position, their undisturbed position, their rest position. When I disturb the particles, they move away from this equilibrium position marked by the dashed line. You can see this one has been displaced less, and this one is displaced the most. Okay, so all of these are a certain distance from the equilibrium, and that's the particle displacement. I'm going to draw it on this graph. The displacement from the equilibrium, so the distance between a certain particle and the equilibrium, that's the particle displacement. Now, when we have a maximum particle displacement at a crest or a trough, that is the delta x max, the maximum displacement of the disturbance of the particles in that disturbance. This is called the amplitude, the maximum displacement above or below the equilibrium point. Okay, and those points of maximum particle displacement above the equilibrium are called crests. So there's a crest, and it looks like there's another crest, and there's another crest. A trough is a point of maximum particle displacement, a point of amplitude below the equilibrium. So here we have a trough, and here's another trough. All right. Now, wavelength, frequency, and period. These are properties of periodic transverse waves. Okay, so we can have a transverse wave pulse, but we can also have a periodic transverse wave like this one. And this is the type of wave that will have a wavelength, period, and frequency. A wave pulse doesn't have any of those properties. So the wavelength is the distance between two crests. So if you took a ruler, you could measure I paused this one, so I could actually take a ruler and I can measure the wavelength of this wave. It's going to be the distance between two crests or two troughs. So this shows you here how to measure one wavelength right there, but you could measure wavelength in a couple of ways. You can measure wavelength from peak to peak also. That would be the wavelength. But you can also, if I choose a point where it crosses the equilibrium, and then I skip a point and I go to the next one, that would be the wavelength. And the distance between two immediate points would be half a wavelength. Okay, so that's three different ways to measure the wavelength. So I can measure the wavelength here. It's about 4.2 centimeters, and I'm going to get the same answer no matter how I measure that wavelength. So I can measure the wavelength from trough to trough, about 4.2 centimeters, or if I choose a point where it crosses the equilibrium, skip the next one, and then go to the next, that's going to give me my wavelength as well, 4.2. Okay, so that's how you would measure wavelength. And of course it's a length, so it would be measured in units of meters or centimeters, some unit of length. Now frequency. Frequency is how many, remember this is a periodic wave, it's how many of these wave pulses that pass a certain point in 1 second. So how many wave pulses pass maybe the 2 centimeter mark every second? Well, I already know, 1.5 hertz. Let's make it a whole number so it's easier to see. So 2 pulses should pass this point every second. So let's try and see if we can count. 1 Mississippi, 1 Mississippi, 1 Mississippi. When I count 1 Mississippi, starting from here to here, that's you get 1 wavelength passes this point every, or 2 wavelengths, or 2 pulses pass this point every second. 1, 2. So 2 wave pulses will pass this point in 1 second. A trough and a crest will pass that point in 1 second. So that's how much time it takes the individual pulses to pass a point in 1 second. Okay, that's the frequency. It's the number of cycles over the amount of time it took for those cycles to pass a certain point. The unit for frequency is 1/seconds, which is also known as hertz. Okay, like the car company, that's how it's pronounced. Alright, but the unit is hertz, or 1/second. It has units of 1/time. That's frequency. Now, period is the inverse of frequency. They're very closely related, but they're inverses. This is how much time it takes for 1 pulse to pass. So if the frequency here is 2 hertz, if 2 pulses pass in a second, then my period is 1/2. If I choose a certain point, half of this wave, which a whole wave would be from here to here, that's the wave, that's 1 wave, the whole wave will pass this point in 1/2 second if the frequency is 2 hertz. So it's kind of hard to see, but how much time it takes 1 wave, not really wave pulse, but the entire wave to pass a certain point, or time it takes for 1 wave cycle. So that would be the inverse of frequency, the amount of time over the number of cycles. And it's a unit, it's a measurement of time, so the unit was usually going to be seconds. Okay? And then furthermore, if you know period, you can get the frequency. And if you know the frequency, you can get the period. They're inverses of one another. And you could get, if you know one, you can always just get the other. Alright, so they're pretty interchangeable with these two formulas. If you know the period, if you know the frequency, do 1/frequency to get the period. If you know the period, do 1/time, 1 divided by the period to get the frequency. Okay, they're inverses of one another.